Now, we are looking at a new design pattern. The pattern name is state, and it is ideally suited for implementing something like the microwave, where we have multiple states in which the finite state machine can be at any given point in time. So we have a situation where we have a number of states as in the microwave, and each state has distinct behavior. And we have a number of external inputs, events to which the system must respond. And all these states are part of the same application. So they have the same context. For example, in the microwave, the states would, of course, be door closed, door open, or cooking, and they have something in common. The purpose being cooking, there is a time left to cook, there is a light, and so on. So there is a context. In those situations, we use the state pattern. So to give you the heads up, in the state pattern, we essentially have one concrete state, one non-abstract state class for each state. In the microwave, for example, we have 3 states. So we are going to have 3 concrete states and a super class for all 3. We will also have a context class. So in this slide, we are talking about what the context is going to be storing. The context always remembers what the current state of the finite state machine is. The states themselves cannot store those. There is no point, really. It won't work. So somebody external to the state classes have to store the reference to the current state object. There should be a way to change the state and record the new state. The context could keep track of other pieces of information. For example, the time left for cooking could be in the context, or there could be other common variables that you need to keep track of. But what it could also contain would be methods for external entities to communicate to the states. So this could be the gateway. The context could be the gateway for external entities to get to the states, to tell states that things have happened, or for the states to tell the external entities. So this is the gateway for external entities and the states to communicate among themselves. We will see that as we explore the code of the microwave. So what are we doing when we create these state classes? If you recall, in the initial implementation of the microwave, we had a structure like this. For the cook requested method, public void cook requested. So this is the event. And we had a conditional like this. If current state, which was a field in the microwave class, is equal to the door closed state, we do one thing. And if it is the cooking state, we do something else. And for the other states, we simply ignore the request, right? Else we don't care. So the behaviors are different. They depend on the state. So what this means is we should replace these conditionals with polymorphism, which means creating one new class per leg. So we should have a class for the door closed state, a class for the cooking state, and what is not seen here is the else part of this, which is the door open state. So that would be the third state. So we create three states using the refactoring rule of replacing conditionals with polymorphism, and we will have a superclass, an abstract class, microwave state, set up like this. Now, we will see the code a bit later. Let's talk about how we can transition between states. We will have three objects, and these will be singletons. There is no need for more than one object of any of these state classes, so they are singletons. And how do you transition from one to the other? There are two ways of doing that. One is to use what is called a centralized representation, and the other one is to use what is called a localized representation. So let's talk about the centralized representation. For this, we use a table. So here is the table that we will have in Java if you were to use this approach, the centralized representation. This is the state transition table of the microwave, the reduced state transition table. And this is the corresponding Java implementation of this table. Let's see how this works. This is a table, right? Two-dimensional entity. So we need a two-dimensional array. So we have int one pair of square brackets for the first dimension. This is for the rows, and the second dimension is for the columns. So we have two pairs of square brackets, and the array name is transitions, and it has all these entries. So this is beginning the array, and this ends the array, and the first or this line here shows what goes into the first row. This line here shows the second row, and this shows the third row. What do these entries mean? Well, what we do is we number these states in any order. Since we have written this state transition table this way, we are going to have 0 for door closed, 1 for door open, and 2 for cooking. So we are just going by the order of states as they appear in this table. It could have been a different order, but it would have been just a little more difficult to fill in this table, and it really doesn't matter in what order we pick them. So we just pick the order that comes very naturally, using 0 for door closed, 1 for door open, and 2 for cooking. Similarly, we are going to assign numbers for each event. 0 for open door, 1 for closed door, etc., and 4 for timer runs out. So this is the row corresponding to, or this is the row in the Java array corresponding to this set of entries. So if you see here, door open is the first entry, and that has a number of 1. So we put that over here. Door closed is 0. So that is the next entry. Cooking is 2. So that is the third one. Door closed is 0. So that is the fourth one. And door closed is again the fifth one. So 0. Similarly, you can work out the values for the subsequent rows. That is the centralized representation. If you have the centralized representation, you would store this table in the context. So the context knows what state to go to when one state finishes its work. Another approach we will see in a minute, but we will have a method like this to change the state within the context. Public void change current state, and in the centralized representation, we will see what the next event is. What is the event? We go to the current states row and extract the entry in the transitions table for the event. And that would be the index of the current state. Here is the second approach. And this is going to use the individual states. They decide what the next state should be. It is not the context that gets to decide, it is the individual states. So, for example, the cooking state has this instance, cooking state dot instance. So you could say microwave context dot instance, that is a microwave context object, ask it to change the current state to cooking state. So this could be done from the door closed state. So notice that here we are having an individual state decide what the next state should be and telling the context. Whereas in the other case, the context gets to know what the next event is and then deciding what the next state should be based on the current state and the event. So those two are different ways of changing the current state. Now, what does a state do? The microwave state is the superclass. It is going to be an abstract class. It will have one method for each event. Cook requested, door closed, door opened, clock ticked, and timer ran out. There are 5 events if you look at the state transition table. And we add 2 more methods. One is the enter method, the other one is the leave method. There may be a few things that you need to do when you get into a state. So before we actually start processing any events within a state, we may need to initialize, we may need to set up some stuff. Maybe we need to start up a timer, or we may need to set a counter to 0, whatever. That is done in the enter method. This is left abstract so that every state has to tell what it needs to do before starting its processing. And before leaving the state, what should happen? That is in the leave method. So this is what we would do in the door closed state. In the door closed state, we need to worry about door being opened and cook request being issued. We don't need to worry about closing the door. So we don't need to worry about the timer ticking or the timer ending the requested time. None of that. So only 2 of these 5 methods need to be overridden here. But the enter and leave are abstract methods in microwave state, so they need to be always overridden.